The resting potential of a neuron is the consistent charge that is maintained in between neural impulses. At this time, sodium-potassium exchange pumps use ATP to ensure a constant charge of approximately -70 millivolts is sustained. It does this by expelling 3 sodium molecules outside the membrane and bringing 2 potassium inside. This happens because naturally sodium and potassium gates can be leaky or defective, therefore throwing off the charge in the membrane, meaning a pump must always be in action to combat this defect. In addition to the pump, negatively charged proteins that cannot pass through the cell membrane help to maintain its negative charge. In order for excitation to occur, a force or a change in the external environment must trigger a sensory nerve ending. If the stimulus is strong enough to reach threshold potential of -55 millivolts, this will trigger an action potential, therefore spurring sodium gates at the site of the excitation to open. After an action potential occurs, sodium gates open and sodium rushes in. This depolarizes the membrane, meaning the charge becomes more positive. At this time, the membrane has a charge of at least -55 millivolts. However, if the charge surpasses this threshold, the response will still be the same as if it were at -55 millivolts. Repolarization occurs as the result of depolarization, and the membranes increase in charge. This triggers potassium gates to open up, allowing potassium ions to leave the membrane and bringing the membrane back to its original charge of -70 millivolts. After the initial repolarization occurs, the potassium gates stay open for too long, letting more and more potassium out of the cell membrane. This results in a state of hyperpolarization, meaning the membrane has overshot its resting potential charge, bringing it to roughly -90 millivolts, which is too negative. In order to combat this hyperpolarization, the sodium-potassium exchange pump starts to work at a faster pace than at resting potential. Using ATP, it excretes 3 sodium ions out of the cell membrane while bringing 2 potassium ions in. During the refractory period, no impulse can occur since its charge is still too negative to reach threshold again. This ensures that the action potential travels in the right direction. Signal propagation is the process in which an action potential travels along the axon of a neuron. Once one area of the axon depolarizes, sodium diffuses a short ways down the axon into the surrounding area where it spurs more sodium gates to open and depolarize the local membrane. This cycle of depolarizing, repolarizing, hyperpolarizing, and so on sequentially occurs down the length of the axon until the neural impulse reaches the axon terminal bulb. Saltatory conduction is the process in a myelinated neuron where a signal travels throughout the axon by means of diffusion. Once triggered, sodium gates open a node of Ranvier and sodium rushes in, therefore depolarizing the local membrane. The sodium diffuses through the myelinated axon until it reaches the next node of Ranvier, which then depolarizes and opens the surrounding sodium gates. The signal only goes in one direction because the previous node of Ranvier is in the refractory period. This process is much faster than signal propagation in unmyelinated neurons. Once the signal reaches the presynaptic axon terminal bulb, small sacs of neurotransmitters called synaptic vesicles bind to its membrane. Through a process called exocytosis, the vesicles release the neurotransmitters into the space between the pre- and postsynaptic neuron, called the synaptic cleft. By means of diffusion, the neurotransmitters reach the postsynaptic membrane where specific receptors receive the signal from the transmitters. This signal can be excitatory or inhibitory. After the neurotransmitters have done their job, they are either broken down by certain enzymes or reabsorbed by the presynaptic membrane.